So, Nikhil, that day we had discussed electric field. Okay, you are not there on the day. We had discussed
Yes,
little
sir.
bit about electric field. Yeah. So, have you read that part or no? Okay. So look, electric field. So when you keep, what is electric field? When you keep a charge, suppose I am taking a positive capital Q charge, okay, and I bring another charge just at r distance, suppose, okay, at r distance, a small q charge, okay. So magnitude also, this magnitude of this small q charge is also very less. Okay, not only I am writing as small letter, but magnitude compared to the capital Q, it is less. So when I do that, what happens? When I bring this small q charge will experience a force, that is coulomb force, right? That we have discussed, coulomb force. And this will be force of repulsion, okay? It will just push like this. And at the same time, small q will push this capital Q in this way. So this is coulomb force. So now the question was, if I just remove this small q, okay, if I remove, when the small q was there, that means another charge was there in this region at r, distance r, it was experiencing a force. But is there anything when I remove the small q charge, when I remove it, when it is not there? So is there anything at this region of space? So is there anything in this region of space? If you say no, it is vacuum, then how come if I bring if I bring another charge, it is experiencing a force. If it is vacuum, it should not have experienced any force. So then the scientists uh, argued that there must be something, and that was actually named as field. Okay, since it is created by electric charge, so it is called electric field. There is something called electric field around this region. So that means if you keep any charge, Q1, Q2, or anything, it will create an electric field around it. If I keep a capital Q charge, so it will create, say in this region, it will create a field around it. Okay, it will create a field, and that field, that is called electric field, we denote with E, and it is a vector, because you know, like force is vector. So, and we measure the electric field as force per unit charge that I'll define. So this electric field is a vector quantity. Okay, that means it has both magnitude and direction. So electric field is actually intermediary, or it is kind of like, see, if air would have not there, we would have not been able to hear sounds, right? If air is not there, means we will not be able to hear sound. What does it mean? It means, see, these two charges, they are interacting between each other via electric field. So electric field produced by this capital Q is acted upon the small q, which is actually creating a force on this small q charge. So do you understand? So it is the electric field which is actually creating a force on the small q charge. Otherwise, see, it is at far distance, like it is at r distance anyway. They don't have bodily contact. So how do they like interact with each other, or how do they uh, exert a force on each other? That is via electric field. Okay, that means if you keep any charge, okay, it will create electric field around it. Okay, it will create electric field around it. Now, how to define electric field? You have seen that electric field, the effect of electric field is seen as force, right, on other charge. So it is the effect of electric field is the force. It applies force on other charge. Okay, so that's why it is defined as electric field is defined as force per unit charge. Force per unit charge. And look here, since this small q charge also will be affecting this uh, like will be repelling this capital Q charge. So the position may not be fixed if so happens. Okay, that means in that case we cannot define the electric field definitely at any point. Okay, because see, if this also pushes the capital Q charge, it may also move from here. So the distance will not be constant. Okay, or the position of the Q will not be constant or undisturbed. So to keep this capital Q charge undisturbed, we bring this small charge very less in magnitude. So the actual definition of electric field would be limit Q tending to 0. Q tending to 0, okay, and it is force per unit charge, okay. Or the if you bring a very tiny charge near a near another charge, okay, that tiny charge will experience a force, and if I say force per unit charge, that will be the electric field, and it has both direction and magnitude. And electric field and the coulomb force, they have the same direction actually, okay, in the same direction. All right, now see the charge capital Q, which is creating a field around it, is called source charge. It is called source charge, okay, source charge. And this is the charge with which we are just testing the presence of the electric field, or we are able to see the presence of or effect of the electric field we see on small q charge. That's why it is called test charge. Test charge. Okay. And as I said, electric field, the magnitude of the electric field will be force per unit charge. So see, force means Q into Q by 4 pi epsilon naught R square. So per unit charge means kept small q down. So this will go up. Excuse me. So you'll get q by 4 pi epsilon naught R square. So this is for a point charge. Okay, this is for a point charge. This is the electric field for a point charge. You will see later sections. We can we can find out the electric field for an extended charge using Gauss's law. That we will learn later section in this chapter. And look, so the electric field, you can see the electric field is depending on the magnitude of the source charge, and it is depending on the distance between the source charge and test charge, but it does not depend on the test charge, because we have no like nowhere I have the small q right in the expression of the electric field. So this is electric field. Okay. Now if you have, so that was single due to single source charge. So at P, I have found out the electric field, that is Q by, if this is R distance, then we have got Q by 4 pi epsilon naught R square. This was the electric field for a single charge. But if you have multiple charges, okay, another charge here. So suppose this is Q1. If you have Q2 over here, in your book, I think they have written small Q1, Q2, okay, and Q3. Like that, if you have Q4, maybe you can take again Q4. So if there are so many charges, and at this particular point, you have to find out the electric field. So how do you find out the electric field? So do you remember we had learned the principle of superposition uh, when we were calculating coulomb force for such multiple charges? What we had stated there, according to superposition principle, you can calculate the electric field for individual charges and vectorially you have to add them so that you get the electric field for all of them. So when you calculate the electric field for the Q1 charge, you have to write only Q1 by 4 pi epsilon naught. Excuse me. Yeah. So R1P square. Okay. At that time, I will not see the presence of, or I will not consider the presence of other charges. Similarly, when I calculate the electric field at P due to Q2, see this is suppose R2P distance. Okay, so I'll write Q2 over here, and here the distance R2P. So then so the resultant electric field will be the vectorial sum. Okay, so if I say this is E1, then E2. Okay, so I have to take the vector sum of all. Okay, then you get the total electric field at P due to all the charges. So this is actually superposition, law of superposition. Okay, depending on that, few examples are there. You can read it. Okay, now so this was the recap part. I now start today's lesson. Okay, today's lesson actually is electric field line. Okay, yeah. So electric field line, as I said, that the electric field is a vector quantity, right? Electric field is a vector quantity. So since it is a vector quantity, we have learned in 11th standard that any vector quantity can be represented by a line along with the arrowhead. So the length of this vector will give you the magnitude of the vector A. Suppose vector A, it will be given. So the length of the line will give you the magnitude, and the arrowhead will give you the direction of the vector, right? So since electric field is also a vector, we can represent the electric field with a line and arrowhead. Okay, with a line arrowhead. So the magnitude will be given by the length of the line, and direction will be given by the arrow. So look, uh, if I say that one point charge is creating electric field, so how the electric field lines will be drawn for that? If it is a positive charge, the electric field lines will be drawn with arrowhead. You can see this is a positive charge, and these are the arrows, and how they are uh, distributed. Actually, this has a spherical symmetry that we will read later, and the electric field lines are radially going out. Okay, radially going out. And how do you define the strength of the electric field? How do you define the strength of the electric field? See, in this representation, so if my uh, density of the field line, so these are called electric field lines. Okay, these are called electric field lines. Okay, these are arrow heads. These are called electric field lines. Obviously, I can suggest electric field. Okay, so this the arrow, when I have the density, greater density of the arrow, the field strength will be more, and when the density of the arrows are less, the electric field will be less stronger. Okay, suppose I have Q positive charge over here, So as you go away from the charge or far from the charge, you look how it happens. If I draw something over here, if I draw something over here. So how is the density of the field line? Now, if you just draw over here, how is the density of the field line or the electric field line? See, in the beginning you look, so there are, see, the electric field lines are actually close this space, right? Electric field lines are close this space. So that's why this will be having greater density at the near to the charges. That means the electric field is stronger near the charges. Okay, near the charge, near the charge. And if you go further and further from the charge, what happens? See, the distance between like the electric field lines they separate all separated. And this separation goes on increasing as you go away from the charge. Look here how they are separated by large distance. So the density of the line are decreasing as you go away from the charges. So that means you can just guess that electric field will be reducing as you go away from the charges. So do you understand this point? From this representation, what you can understand is as you go away from the charges, the field strength of the field decreases because the density of the field line decreases. The field lines are all separated away from the charge. Now look, the same thing has been discussed in this particular figure. So this particular figure, you look here. Are you able to see this figure, or I'll bring it to the left side a little bit?
I can
This
see,
particular
sir.
figure, are you able to see? Okay. Okay then. See, I have a pointer small q at the origin, suppose O, and see, as I said, the electric field lines will be going like this, okay, like this, radially outward. Now I need to know where the strength of the electric field will be more and where less. So if I take two small rectangular area, look here, this is R and this is S. These two areas are same, okay, areas are same. But when I have hold it actually at this position, I'm holding it. See, the number of field lines crossing this area are 3, 1, 2, and 3. And when I keep that same area at this position, look here, how many lines, like electric field lines, are crossing this area? Hardly one. Okay, do you understand? Okay, that means the electric field lines are all separated. So the strength of the electric field is more here, stronger region of field here, and this is region of weak field. That's why it is called region of weak field. That means as you go away from the electric field, sorry, away from the charge, the electric field strength decreases. Now you might be thinking, sir, from this representation, see, we have seen from the Coulomb law that electric field depends on 1 by r square. 1 by r square. So from this representation, whether we will be able to understand the strength of the electric field varying with 1 by r square. Whether it is understandable from here, or you can say whether electric field. Yeah, in this representation, we can see the electric field is varying with 1 by r square. The answer is yes. You can see from here. So there is something called solid angle. Okay, there is something called solid angle. What is that? Solid angle. You have learned, yeah, you have learned two-dimensional angle. Okay, two-dimensional angle. How? This is one card part. Okay, and suppose this curve makes an angle theta over here. So this is suppose having a radius r, and this is theta, or maybe I'll say L, okay, and theta. See, oh, sorry, this is angle theta. Suppose this is the r and this is L. So what I can say, theta is actually theta will be L by r, right? That is what we know, right? The arc length divided by the radius, that is the angle, right? So this is actually in 2 dimension, okay? 2 dimension, okay? Or yeah, so this is the 2-dimensional angle. But there is something called solid angle, which is 3-dimensional angle. So you can see here that the angle depends on 1 by r, 2-dimensional angle or linear angle, I can say this one depends on 1 by r, okay? Or in the numerator you have only the arc length, only the arc length. But suppose I have a sphere like this, okay? I cut a solid sphere, okay? Solid sphere means it has mass. Solid sphere on good example is actually shot football. You know shot football, that is very heavy, right? Because that is actually concrete. Uh, yeah, it has mass everywhere inside, okay? Compact. So now if I draw a cone from here, like this cone, okay? So with this surface, look here. That means this is the surface. This is the surface. Like this is a surface which is making an angle at the center. Okay, this is called solid angle. So this is a surface. No longer this is a line, right? Here theta is equal to L, the arc length by radius. So this is a line, but here it is actually ds, the area element. Okay, and this is denoted as actually delta omega. Okay, delta omega. So elemental solid angle. So do you understand? Solid angle actually is subtended by an area at a certain point. Okay, at a certain point. If I have an object like this, so if I just uh, add the edges, the point of the edges to a point, 2 points at the edges to a common point, then this area will make an angle which will be called as solid angle. This is denoted by omega, d omega, delta omega. So the d omega or delta omega, whatever you can say. Okay. If I keep, so you can understand that if I keep any object, it can make an angle, solid angle at a distance. Uh, if you add the 2 points at the edges of the periphery of the surface, right? So it will make a solid angle. So solid angle then defined as d omega is equal to ds by r square. Okay, ds by r square. This is how solid angle is defined. Okay, do you understand what is solid angle? Solid angle is the angle subtended by an area to a point. Okay, at a point, by an area at a point. Okay, so this is the area which is making an angle or subtending an angle at a point P sub or O. In this case, it is shown here O. And see, here it is written the d omega is a solid angle. And this is 2-dimensional angle, okay? No longer a linear angle. That is L by R. It is not that, okay? And look here. So here it was length by length. Here it is area by R square, right? Area by R square. So that's why. So this ratio will be having always dimensional. This is a dimensionless, in a sense like it is radian, obviously. But if you just go with the length, this is the ratio of length by length. In this case, area by area, okay, or the dimension of area, R square. So this is how the solid angle is defined. Now, in your book, it is said that if I take two such area, P1 and P2, Look, for P1, the distance is see R1 suppose. Okay, it is at R1 distance. So what will be the solid angle? What will be the solid angle? Actually, solid angle is the same. Solid angle is the same for both the surfaces P1 and P2. But the surface is, if d omega by R1 square, suppose this is actually ds1 or P1. Okay, at P1. Okay, and at P2 the surface is d omega. The solid angle remains always constant. Okay, solid angle, see, this remains always constant. Okay, this is the maximum area you can have with this solid angle. Okay, you can have another area over here which can have the same solid angle. Okay, you can have another area over here with the same solid angle. Okay, so here P1 and P2 areas, look here, the two areas, they are at different distance. So the solid angle by R2 square will be ds2. Okay, so I'm sorry. Actually, this will be multiplied R1 square, and this will be R2 square multiplied because our solid angle definition of solid angle was uh, ds by R square is equal to d omega. This was my definition. So according to that, the area, you look, the solid angles are same, but same solid angle will be subtended by different area. See, the ds1 is equal to R1 square delta omega, right? And d2 ds2 is actually, see, this one R2 will be in the numerator only, so denominator will not be there. So this is the area. See, look here, the area is actually increasing, whereas the solid angle remains the same. Solid angle remains the same. And you look the number of field lines at this region P, the density of the field line is much more than this place at P2. See, understand, right? The density of the area has increased, but the number of how do I say density? Density, you have to say some number by volume or some number by area. So look, this number, the number of field lines remains the same. Here, if I say number like surface density of field line, the number remains the same, but this area ds2 is becoming greater than ds1. That's why the field strength decreases. Uh, decreases as you go away from the point charge Q. So field strength will be more here at this P1 and less over here. And how does it vary? It vary with 1 by R square. So from this solid angle concept, you can understand that the electric field actually is varying as 1 by R square. Okay, you can have an intuitive idea from here. Okay, so this is what has been discussed a bit more in your book. You can just read that. So this was the sum and substance of this part. Now we'll see. See, I have just covered. Okay, I just talk about few more things here. So I was saying you that the electric field lines will be always radially outward for positive charges, and for negative charge, how it will be, how you define or like how you denote the electric field line. It is actually radially inward. Okay, radially inward for a point, negative point charge. Okay, it will be radially inward. Okay, this way also like that, radially inward. So for positive charge, how it is radially outward. This is how we will denote the electric field created by positive and negative charges. Okay, if I keep positive and negative charges near to each other, look how it will be. See, negative, for negative charges, the field lines will be actually uh, coming in, right? So your electric field will start from here and then go into here. Okay. So field line direction will be like this. Okay. Field lines will be like this. And from outwards also it will be coming like this. And in this case it will go even this way also, even in this way, like that. Okay, this way it will go out. Okay, this is how field lines will be drawn in case of positive and negative charges together. If you have both the positive charges together or negative charges together, they will be repelling each other. So what will happen? The electric field will be like this. So there will be a gap between them because they will be repelling each other. Okay, so this will be an empty space. So here at in between this point, there will be no field. Okay, field will be cancelled by each other if the charges are both equal in the magnitude. Okay, so this is about the field lines produced by electric and uh, sorry, positive and negative charges. Okay, now we'll see. Uh, yeah, so we have discussed up to you will be able to see here. Okay, positive charge, negative charges. Okay, so now we'll see a new term over here called electric flux. Do you know what is the flux of water in your bathroom, toilet, and everywhere? The water line is there, right? Water is coming by tube, okay, pipe, okay, water pipe like this. Suppose I have a pipe of 1 meter, okay, 1 meter, and see this has area A, okay, and the water is actually flowing in this way with velocity v, okay, with velocity v. Can you tell me how much in 1 second? In 1 second, how much water will flow? How much amount of water will flow through this? Okay, can you tell me how much water? How much amount of water? Priyadashini?
Sir,
Yeah, how much outflow of water will be there in 1 second? If the velocity, see this is the velocity v per second, v meter per second suppose, okay, velocity of the water.
one.
So how much amount of, yeah, one, that means the volume, that means the volume of this, right? Volume of this, right?
Yes, 1 milliliter, sir.
That means, sorry. No, see the I have not given you any number. Okay, so look, that volume of this water will be A into 1 meter means one, obviously one, and this is v is the velocity. In fact, actually, see, in 1 second means you can just write A into V. That will be the flux. This will be outflow of water. Outflow of water. Okay, outflow of water in a second. You understand this or not? What is the volume in 1 second? In 1 second, suppose it goes g meter per g meter in 1 second. Okay, that means okay, just ignore the base of this. So it goes g meter. Okay, and what is the area? So area into the length is goes by 1 second. So area of cross section is everywhere same. Okay, and how much it travels in 1 second is v. That is the length. Okay, so you have a water column like this. Okay, you have a water column, cylindrical water column like this, which has area, that area A, and length is this. So you have the volume of this water column, that is A into L, right? So L is nothing but here A into B. This is the velocity. So do you understand that this is the outflow of water? This outflow of water is called water flux. What is that called? Water flux. What is this called? Water flux. So you can see the water is flowing perpendicular to the surface, right? Perpendicular to this surface. So, so this water, see, water is flowing this way, right? That means perpendicular to the area, right? Perpendicular to the area. Perpendicular to the area. Okay. So we'll see in your book it is written nicely what is called water flux. And once you understand what is water flux, then we'll be able to understand what is electric flux. So consider flow of liquid with velocity v through a small flat surface here. Suppose they have taken flat surface, okay, in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing per unit time. Understand? Crossing per unit time. So it is the volume, right? It is the volume crossing per unit will be the amount of water, or flow of liquid, or flow of water through that surface. And see the water is flowing normal to the surface area. Okay. So then you can just multiply the v velocity into the area per unit time. This is per unit time. Otherwise, you have to write the length. Okay, v into t will be the length. So this is the per unit time. This is the outflow of water or the flow of liquid through the surface. Okay, and it is given by the volume crossing per unit area, per unit time. Sorry. So volume crossing per unit time, and it is actually called as flux of liquid, which is flowing across the plane. Flowing across means I'll tell you what is across and what is tangential. So across means this is okay. So this is, suppose this is the area. It is perpendicular to the suppose perpendicular to your page, okay, and then your water flow is happening through this, okay. This going like this. So this is across. That means if you have this is the area, if this goes normal to the area, then this across flowing across. This is called across. Right? This is across. Okay. If I say flowing like this is tangential. Okay. This is tangential. This is not across. Tangential. But see the flux in the definition will be using only the across. Okay, across part. The water flowing across, the electric field flowing across, that will give you the flux. And across means normal to the surface. So that is what I wanted to say. Now see there is another point. So we'll be learning again. So that is actually the area normal. If the flux, if the electric field line, see if the electric field lines are parallel to the outward normal to the surface. Suppose this is the surface. So outward normal means this way. So area also can be a vector. Area can be said as area vector also. Area can be termed as area vector. So what does it mean? That means area has actually certain amount of magnitude as well as direction. So how do you define the direction of the area? The direction of the area is actually the outward normal to the surface. Okay. Suppose you have
Perpendicular to surface, sir.
exactly not only perpendicular, it has to be outward. Suppose I have a plane like this. Okay. So I'll not say this way. I'll say outward means this way. Okay. Outward normal, you have to say. Outward normal. For this surface, suppose you have what to say, you have a brick. Okay, so it is little bit thick, right? You have brick means you have two surfaces, right? This is one surface, another surface is this way. In fact, yeah. So when you have two surfaces, okay, I'll just draw it in this way. So when you have two surfaces here, in fact there are six surfaces. If I take this is the surface, this is one surface, another parallel surface is this one. So what will be the like normal, like area normal or direction of the area? For this surface it will be this way, and for this surface it will be this way. Okay, for a book, you have a book, right? You have a book, you have two surfaces. Okay, one is along the left hand side, another one is right hand side. So how do you write the area normal? So area normal is the normal to the surface area, and but that has to be outward. Okay, that should not be inward. It is not this way, or this is not this way. This is actually the correct one is this. This one, this is denoted by n cap. Okay, so I have a surface area like this. Uh, so normal will be this way. Okay, not this way. This is not correct. This is the correct outward normal. That is the direction of the area. Okay, so now see, if I have electric field like this, they're coming parallel to so parallel. So this is uniform electric field. Suppose uniform electric field. Uniform electric field is denoted by equispaced parallel lines. Okay, equispaced parallel lines. Okay, this is uniform electric field. So if this electric fields are passing across or crossing across an area, across means an area, this is perpendicular to the, and this area has actually area is perpendicular to the electric field like this. If they are passing through, see, area normal is also along this direction. Okay, so what we define actually electric field, sorry, flux. Electric flux is defined as electric flux is defined
Zero,
is
sir.
defined as no. Electric field is no. I'll tell you, not zero. It is the maximum actually. I'll tell you. E dot ds dot product with the dot product. Okay, electric field E electric field. See, this is the ds means if suppose at dot ds. That means this has the magnitude ds area. Magnitude of the area is ds. Okay, and it has, we have put arrowhead. That means ds is the area vector. Okay, area. So what is the direction of the area and what is the direction of electric field? Okay, in general it will be E ds cos theta, right? Cos theta. It is a scalar product, cos theta. So that theta is the angle between electric field. So this theta is the angle between electric field and ds, the area normal. Okay. So area normal is along this way. If I say n cap is the direction of area normal and this is the electric field. In this case, the electric field and the area normal is in the same direction. Right? So you see E area, electric field and this area normal, they are parallel to each other, right? So what is the angle between them? Angle is zero. So the electric flux is ds. So this is the maximum field. But suppose, so do you understand Priyodashini, Nikhil? Do you understand how do you define electric field? Actually, if I have a bigger area, so I have to take the summation over it. Okay, if I have many surfaces, I have to take summation over it. Okay, this I can even write in this way: E ds E dot n cap ds. Okay, n cap is the direction of the area. and this is magnitude ds. So E dot n cap ds, I'll just clean it and write. So when you have many such small area, so you can write as a summation. Okay, as a summation you can write E dot n cap ds. N cap is the direction of the area normal. Okay, outward normal is the outward normal of the surface area. Okay, so now look, if the electric field is not exactly parallel to the area normal. Suppose my area normal is in this way, n cap. Okay, so suppose my area is like this now, like this, but my electric field lines are like this. So they have an angle theta. This is theta. Okay, so this has ds in this direction, ds vector in this direction. So then it will be E ds cos theta, as I said. Okay, so it will be, it depends on, so you look here. So what is the definition of the electric flux? That is the electric field lines passing or crossing across just a minute. Electric field line passing through an area perpendicular to it. Okay, right. Through an area perpendicular to the direction of the field. So the area is perpendicular to, so in the definition you can see the electric field lines passing through, passing through an area which is perpendicular to the direction of the electric field. That means when we don't have electric area perpendicular to the electric field, I have to take the component of the electric field along the direction of area. So you have to take E cos theta in that case. Okay, and E sin theta along this way will not give you any flux. It will give flux in this way. So E cos theta you have to take E cos theta ds in that case. Okay, so that's how you get E dot ds. Understand? You get E dot ds in this way. Okay, I should have written this first, then I will written the formula. So electric flux is denoted by phi, and it is actually summation E cap d dot ds. If you have many small area like the ds and all. Okay, so this is the summation, and sometimes people write electric flux so phi E. They denote this because magnetic field also will denote the magnetic flux also we denote as phi. So to distinguish that, electric flux is denoted by phi with suffix E. Okay. Now look, we will go through your book little bit. So we have to take the component of the electric field towards the area normal. Okay, that will give you the electric flux. So look here. See the electric flux, like electric fields are passing normal to the passing through the area which is normal to the electric field, and when you don't have area which is normal to electric field, that means the area direction of the area vector, that means the n cap will not be along the electric field. For that case, you have to take the component of the electric field. Okay, then you get the flux due to that. Okay, you get flux due to the normal component of the electric field, not the tangential component. Okay. So now I'll just give you a simple question. Let me see whether you can answer. Just a minute. Yeah. Suppose I have electric field in this way along the x-axis. Okay. Along the x-axis. This is y. X. This is y. Okay. Along the x-axis. So if I have a cube, or yeah, so I have a cube. Suppose in this way. So which have area, see, 6 faces are there. The 6 faces in a cube, right? So the flux will be counted for which surfaces? Only for 2 surfaces which are perpendicular to the electric field, right? That means if I say this is y, this is x, and this is z. In fact, you will find out electric field for yz faces, right? This face will be perpendicular. Okay, this is z. So yz face will be perpendicular to the x. So you will get electric flux for yz parallel plane. Okay. For other planes or other surfaces, you will not get the flux. Okay, this is another point. And look, I have given you that the flux ds is actually given by E. Okay, E dot ds. So what is the maximum flux? When it will be maximum flux and minimum flux? Can you tell me, Nikhil, when the flux will be maximum and when it will be minimum? So this is nothing but E ds cos theta.
1, sir.
Yeah. So when cos theta is equal to 1, that time it will be maximum. That means when theta is equal to 0, right? When theta is equal to 0. Okay. That means electric field and area, they are parallel to each other. Okay. Now when it will be minimum? Minimum, see, when theta cos theta value will be 0. That time. So what is the condition? Theta is 90 degree, right? Pi by 2 or 90 degree. That means, look at the example I have given that time. That suppose I have area like this. Okay, I have area like this. So area normal is in this way, but my electric fields are like this. Okay, if I break component of electric field, so the electric field parallel to this will give you the flux, or the maximum flux. Okay, than any other component. Okay, which is parallel to this. So E cos theta will give you maximum flux. But what about this one? E sin theta. Okay, that is normal, right? That will give you 0 flux. Okay, this component will give you 0 flux because it is normal to the area. Okay, electric field, sorry, not area, the direction of the area. Okay, if you have n cap and electric field are perpendicular, then you will get 0 flux. Okay, 0. And that happens when the electric field and the area are parallel to each other. This is E and this is area. Okay, if these are parallel to each other, see their area normal is in this way, so that means it is perpendicular to the electric field. So that is what I was telling you. If the electric fields are along x-axis direction, okay, and your like surface area is in the other 2 directions, like y z plane, this one. So that will give you the electric flux. But this x1 plane, this plane alone, okay, this plane and ZX plane, these two planes will not give you electric flux because those are parallel to the electric. Okay, so as you go along with the text, you will understand better much. Okay, much better you will understand. So, the minimum flux will be 0 and maximum will be EDS. Okay. Okay, so this is what I have discussed so far. And see, if you don't have any regular surface area, you can take small area and then uh, sum the flux of all the area, flux to all the area. So see, this is what I have written: the summation over ADS. Understand? This is called electric flux. Okay. Do you understand what is electric flux? Okay. If you read this
Yes.
question, if you don't understand, yeah, if you don't understand, then I'll repeat again. Okay. Yeah. Now I'll just give you a little bit of introduction of electric dipole. Okay, and what is dipole moment and all. Okay, and then if I go 15 more minutes, will you mind? Because it is already 7. If I go for 15 or 10 more minutes.
We can see tomorrow on Sunday, sir.
Sorry, Sunday. Sorry. I did not get. Okay, let me just give you a brief introduction about dipole, electric dipole. Then I'll stop it. Okay, 5 minutes, just 5 minutes. I'll just give you a brief introduction about electric dipole, and then we'll continue with that on Sunday. Okay. So if you have an opposite charges, suppose you have positive Q charge and another charge which is having equal magnitude but opposite polarity. Okay, positive and negative. Okay. If you have such two charges as a pair, and they are separated by a distance. Okay? They are separated by a distance. In your book, it is written 2a. Then these two together will be called as electric dipole. Electric dipole. Di means two, pole. There are two polarities. Okay, electric dipole. So this is electric dipole. When there are equal two charges with equal and opposite magnitude and separated by a distance, then these two are called electric. This will constitute uh, an electric dipole. And the dipole moment, the electric dipole has a dipole moment which is denoted by P, and it is a vector quantity. This is a vector quantity. Why? See, this dipole moment is actually defined as the magnitude of any of the charges into the distance of separation. Okay, that is 2a. So in fact, 2aq is called the dipole moment, and this is a vector quantity because this distance, I can say, this is actually this has certain direction, and see the dipole moment is directed always from negative to positive. So dipole moment has a direction from negative to positive, like this. This is dipole moment. But electric field has direction actually always from positive to negative side. That you have seen already. Okay. Okay. So yeah. So this is okay. So this is called dipole, and P is the dipole moment, and it is denoted by 2aq. So this is called dipole moment. So we'll see in our later section, we'll be asked to calculate the electric field for this dipole. Okay, for this dipole, we have to find out electric field at any point on the axis. On the axis means the point parallel to the direction of the if you just extend the extend this with the dotted line. So this is the axis of dipole. So that is called axis of dipole. That means that is parallel to the direction of the dipole. Okay, this is actually the axis of dipole. So you will be asked to find out electric field at any point. Suppose this is P, okay, on the axis of the dipole. And sometimes they will ask to find out the electric field. Suppose this is the middle point. So you will be asked to find out electric field at a point P, which is on the perpendicular bisector of this dipole. So this is the perpendicular bisector. Sorry, explain it. So suppose this is so perpendicular bisector is this way. So this is P. You have to find out the electric field due to this due to this dipole at this point P, which is on the perpendicular bisector. Okay, is the point perpendicular perpendicular bisector. And sometimes they will ask you to find out electric field on the axis of the dipole. That is any point here or maybe here, I can say. Okay, so that we will see. Okay, how to calculate the electric field. I think I have left. I forgot to discuss the properties of the electric field lines, right? Electric field lines. Okay, this I'll just discuss on the next day. On the Sunday, I'll just discuss a little bit of the properties of electric field lines, and then I'll go to the dipole part again. Okay, so I think then we'll stop it here for today, and we are meeting on Sunday, right? Is that all right?
Yes, sir.
Nikhil? So today we'll stop it here, and on Sunday we'll discuss this. See, I have actually missed out the properties of the electric field line. That those things I'll discuss, and then we'll go to the dipole part. As I have given the instruction of the dipole, that they will find out the electric field at any point on the axis of the dipole and at any point which is on the perpendicular bisector. Okay, in the plane. This is called meridian plane. Okay, meridian plane. The meridian plane. What is the electric field? So this part will be really very much important. Like in your exam, there may be a question like write any three properties of electric field lines, and then they will ask you to find electric field at any point on the perpendicular bisector of the dipole. So those things will be again uh, very important that we'll learn on Sunday. Okay, so we'll stop it here. Okay, see you on Sunday then. Bye for today.
Thank you, sir.